Hello everybody and welcome to the 10.4 notes part 2, which is about finding the lengths of the common internal and external tangents. And I'll show you in a minute what that means again, but a reminder from the previous lesson that a tangent line touches the circle one time. And so if I drew a quick little picture, if this is a tangent line, remember that this point is called the point of tangency. So just a quick thing from 10.4 part 1. If we look at a specific picture here, a common internal tangent and common external tangent really differ just based on where the point of tangency is, meaning both of these are defined by looking at the segment connecting the centers of the circles first. So if I drew the centers and I drew a segment that connects those centers, a common external tangent does not go through that segment. So if I had a point of tangency here and a point of tangency here, this would be an example of a common external tangent. And our goal for the day is to figure out what that length is eventually. And yes, this segment is a line, so it could continue in both directions, but because we actually want to find this length, we're calling it a segment in this section. A common internal tangent does go through the segment connecting the centers. So if with the best of my ability on this screen, I drew a line that looks like it hits this circle one time and then hits this circle one time, there would be a point of tangency and there would be a point of tangency. This would be called a common internal tangent. And so your goal for this section would be to find the length of just this piece, because that's the segment. It goes from point of tangency to point of tangency. And in order to find this length of an internal tangent or that length of an external tangent, there's a particular procedure that the textbook suggests you follow. And that is copied on for you onto your notes from the textbook. It's called the common tangent procedure. Go figure, right? So this is a procedure that I would highly suggest going exactly in the order. And I've tried to do it in the past without this order, and it does not work as well. And so no matter what, when you're trying to find one of the tangent lines, you always want to draw the segment joining the centers first. Then you want to draw the radii to the points of contact, and another name for that is the points of tangency. The third one is probably the most important that you pay attention to. Through the center of the smaller circle, or you could even say from the center of the smaller circle, you want to draw a line parallel to the common tangent. And then eventually you're going to see that this line that we draw will eventually form a rectangle and a right triangle. And so the point of this procedure is to create things that we are familiar with, like a rectangle or right triangle. And then because we have a right triangle, the Pythagorean theorem will come and help us. And so my goal for this first problem is to find this length of this common external tangent. And so the first thing I want to do is draw a segment joining the centers. So I'm going to connect Q and P. Now the radii are already drawn for us, but just to follow the procedure, I'm going to draw the radii to the points of contact. And because this is a radius to a tangent line, this is a right angle. Radius to a tangent line, this is a right angle. So step 1 done, step 2 done. Step 3, from the center of the smaller circle, so P, we want to draw a line parallel to the common tangent. So in this case, that means we start at the smaller center of P. We need to draw a line parallel to the common tangent AB. So I'm going to draw it to make it look parallel. And because I created these two shapes, a quadrilateral and a triangle, I noticed that this quadrilateral has two right angles, which means that this entire thing must be a rectangle. So I created a rectangle and a triangle. If this is a right angle, these are supplementary, so this angle also must be right. That will help our cause, because now let's look at what we actually have, and we're going to probably use the Pythagorean theorem. And so This radius here is 8. So that means that this part must also be 8 because opposite sides of a rectangle are congruent. If this entire radius is 18, again, apologize for the scale on this, but that means that this little piece would have to be 10 because of 18 minus 8. Now, my goal is to find the common external tangent. If I find this segment here, I'm automatically going to find the AB. If I look at this triangle, it doesn't look like I have enough yet to use the Pythagorean theorem, until I remember that QP is made up of 2 sets of radii. This segment has to also be 18 because this radius is 18. And this segment must also be 8 because this radius is 8, which means that this entire segment must be 26. And so in black here, if I focus on just this little right triangle, and I can draw it over here also, we have this being 10, this being 26, and we would like to find this piece. This is a 5, 12, 13 triple multiplied by 2, so x must be 24. So AB, being parallel and equal to x, must be 24 units. So the key to this problem was not only following the procedure, but here noticing that this segment was made up of 2 radii. So sometimes that does come into play. Next example, kept the procedure here. Find GE if the radius is 5 in circle D and the radius is 3 in circle F when the circles are 10 units apart at the centers. So the first thing I want to do in this procedure is draw the segment joining the centers. So I will. I'm going to draw segment FD. And this problem told me that the circles are 10 units apart at the centers. So this segment I just drew here has to be 10 units long. The next thing it wants me to do in this procedure is draw the radii to the points of contact, meaning points of tangency. So if I look at circle D here, if I drew from D to G, this is a radius to a tangent line, an internal tangent to be specific, so it is a right angle. And then in circle F, if I go from F to E, this is a right angle because I have a radius to a tangent line. Now this time my picture looks a lot different than the previous one because my tangent line is interior or internal instead of external. And my goal is to figure out that length. Here's where following the procedure is very important, because if I look at step 3, we want to start from the center of the smaller circle. So from F, I want to draw a line that looks parallel to the common tangent. So this time, my common tangent is here. So from the smaller circle, I want to draw a line that is parallel to EG. And then because I'm just a creature of habit, let's go ahead and connect these. And so again, I have a rectangle that I created. And strangely enough, I have a very giant right triangle here. So let's fill in what else we know. We know that the radius is 5 in circle D. So that's 5. We know that the radius in circle F is 3. So I know that this piece is 3, which means that this piece of my rectangle must also be 3. I know that this entire segment that I'll redo in black, this segment, this whole thing is 10. So this time you need to change your perspective. I did create a rectangle, so I knew that these two were equal, but if I just use, a different color again, I want you to focus on this giant triangle. Now, I know that this giant triangle has to be right because this is a rectangle also within. And in this giant purple triangle, I have this side in its entirety being 8 units. I have the hypotenuse being 10. So this piece here must be 6. And if this piece is 6, it means that your common internal tangent EG must also be 6. So EG is 6 units. And feel free, if you want to pause the video and you want to try this problem again and hear me talk about it again, you're more than welcome to do so. But let me reiterate if you still need it. So the first thing I did was I connected the centers. I drew my radii to the points of contact. I then followed step 3, and through the center of my smaller circle, I drew a line that was parallel to the common tangent that was already there. I made a rectangle. Notice that these two sides both had to be 3. This radius was given as 5, which meant that this entire side of this big triangle was 8. The hypotenuse was 10, so I used Pythagorean triples to get 6. And if this segment is 6, these two are congruent, so that's 6 as well. The last example, what I would like you to do is, this one I'd say is the most similar to the one we just did. So I would like you to follow the procedure, connect the centers. I want you to draw the points of tangency. But first, my goal is to find the common internal tangent. So what we want to do is draw that to the best of our ability. We want to draw a line that hits both circles in one place. So let's draw it like this. There's a point of tangency and there's a point of tangency. So if you could pause your video and try to get as far as you can with this, I'm at least going to draw the picture and I want you to see how far you can get. And I'm going to come back with some of my work done. So please pause now. So guys, I want to check in with you to see if you labeled things correctly so far. First thing you should have done in your procedure is connect the centers, and I did that in red. The next thing you should have done in your procedure is go from the center and draw a radius to the point of tangency. So I did that here and named it 4, and I did that from the center to the point of tangency, called that 10. So my next move is to, from the smaller circle center, draw a line that is parallel to the tangent that you want to find. So because I'm trying to find this common internal tangent, that is in blue right now. So to the best of my ability, I'm going to draw a line from the smaller circle center, parallel to that blue line. And then because I want to make a rectangle, I'm just going to connect it down like that. And I'm going to try to even be a little bit more neat about that. Connect it down. And let me erase this piece here. So now what I did was I created a rectangle, which means I know that these two are right angles here, and I know that these two are right angles here. I know that because this is 4, this piece is 4 as well, which means that this entire side is 14. My goal is to find the blue, and again, I'm just going to use a different color, and I would like you to focus on this giant triangle here. We know that this black piece was given to me as 17. We know that this piece is 14. So this entire piece here, if we find it, we're going to know the blue automatically. So again, if I kind of redraw what's going on, we have 14 here, 17 here, and we're trying to find this. This isn't a triple, so we have to use Pythagorean theorem. X squared plus 14 squared equals 17 squared. X squared plus 196 equals 289. So this would be x squared equals 93. Take the square root. 93 cannot be split. So my answer for x would be the square root of 93, which means my answer is also the square root of 93. Even though I originally didn't give you room for this, what I would like you to do is take the exact same problem, but instead of finding the common internal tangent, I would like you to draw the common external tangent and try that. Here's what the external tangent could look like. Something like this. And so what I'd like you to do is pause your video, try this one completely, and I will come back with my work and my answer. Suggestion would be looking at the first example we did in the notes. So please pause now. And just so you know, your answer will have a square root in it. Pretty giant number, that's a square root. So please try it. Alright guys, so my final answer was the square root of 253. Because once I drew in my radii and I connected my centers, I had a rectangle that I formed because I went from the smaller center circle to the other side, knew that both sides were 4, this whole radius was 10, so this piece was 6, looked at this little triangle and had a blank 6, 17, so Pythags.